Now, this next section deals with diminishing intrinsic properties. If our observable space is in motion within an unobserved space that is also expanding, according to the same geometry that observable space is expanding, then the velocity of unobserved space must diminish with the passage of time. This diminishing velocity along the unobserved dimension must also diminish the intrinsic properties of inertia, the intrinsic energy of a mass at rest, the speed of light, and a formative process that defines the wavelength of a photon. There are also additional changes associated with dynamic systems that depend on a balance between what are called inertial and what I call spatial forces, and I'll describe that in a little bit. Now, since the mathematics is basically the same, I won't go through that, the same derivation of how velocities and all that would change within an unobserved space. Okay, now this represents how the inertial property of mass would diminish over the course of time, how the speed of light would vary. Now, this is all associated with the dimension along the motion along the unobserved dimension. So it's interesting that at the speed of light is the common ground where observable space and unobserved space intersect. And then we also have the intrinsic rest energy of a mass, since this would predict it to vary along an intrinsic property due to associated with this velocity along the unobserved dimension. Since this is diminishing, this would change over the course of time. Similarly, since there is an accelerative field associated with as you're diminishing your velocity along the unobserved dimension, there would be a kind of intrinsic deceleration that would vary over the course of time. Now, having the property of inertia diminish over time was kind of worrisome, like directly attributing the property of inertia to the velocity along the unobserved dimension. Troubled me, since the velocity is proportional to the geometrically the decrease with the passage of time, which requires the property of inertia to diminish over time. Now, the very perfect structure, the expansion of observable space preserved in orbiting systems bound by gravity and charge, would now be destroyed as inertial mass decreases. The effect of the forces of gravity and charge would draw their orbiting masses inward. Orbiting systems would collapse. Rotating galaxies would compress. Atoms contract. And then I must say that it was with some reluctance that the proposed extra-dimensional expansion was added to the model. It should be noted that such collapse of dynamic structure occurs very slowly over cosmological interval times, and that changes observed locally would be extremely difficult to detect. One somewhat reassuring aspect of that is that as astronomical measures defined by gravity collapse, so would the orbital relationships defined by charge. Matter would essentially shrink the same proportional amount, and local measures of astronomical relationships would appear to remain the same, at least locally. Now let's get to as a result of this, we have what I call a non-equivalency of inertial mass and spatial mass. It is generally assumed that the mass associated with gravitational or charge-based forces is the same as the mass associated with inertial forces. This is a big assumption, especially when one considers the vastly different causes for the creation of a force. Inertial mass produces a force when there is a change in the direction or the magnitude of the object's velocity. Gravitational mass produces a force by the relationship the object has with the field structure of space-time around it, interacting with the field structure imposed by another mass on the structure of space-time around it. Similarly, the same effect exists with electrostatic mass and electrostatic charge and their field-based relationships. As seen within observable space, an inertial force requires a change in velocity, while a spatial force exists as a result of a spatial interaction between a mass and the shape of the space-time field around the mass. Now, let's look at that over here. So, if we in observable space, or in the past, and we expand the field-based relationships, this could be gravity or charge, we would see that proportionally everything has stayed the same. But now, so the field-based relationships associated with gravity and charge are maintaining their proportional relationship in this expansion. However, inertial-based forces are not, since if this was an orbiting electron and it loses its inertial mass, the force of charge would become greater and orbits would start to collapse. And that's what I begin to derive over here. Here we have the inertial mass varies over the time. And in fact, here we have the force associated with spatial forces is supposed to vary to the 4/3 power. Yet when we go through the inertial forces and how they would vary, we can see that they're going to vary to the -5/3 power, so they're no longer maintaining their balance. Orbiting systems are going to collapse. This was kind of disastrous when I first started thinking about it. So now we got to consider what happens when orbital systems start to collapse. Actually, any system in which there's a balance between spatial and inertial forces. While I use the word orbital, I mean any relationship that is defined by a balance between spatial and inertial type forces. So first we have to consider there's a conservation of momentum, let's say an angular momentum, although I prefer now I have to kind of differentiate it since momentum is usually associated with the inertia of the object. We now have to think of more of a conservation of motion principle. And if we so rotational intervals is velocity times the radius before is going to equal the velocity times the radius after. So rotational intervals in relative space, and they're also got the same relationships associated within observable space. Sorry about that. Now, if we equate centrifugal force equals gravitational force, and we incorporate the relationships of one in the past and in the future, and we solve for how the measurements of if the inertial mass varies, we can have how the radius of the orbit is going to change, and we're going to have the velocity of the objects are going to change. So, and we end up with this following set of relationships, and they all vary, and you can see how the mass of the objects, the radius of the orbit, the velocity of the orbit, notice it's got the inverse one over here, all vary to the t to the 1/3 power absolute ratio time. So we're predicting how the behavior of orbital systems or dynamic relationships are going to change. And here I've kind of written a summary of the relationships, kind of like there, for orbital relationships. And remember, also in terms of, if you want to think of it, special relativity, that v, the gamma factor, that velocity, the v term or the c term, maintains those relationships. I don't have to consider them because they're being maintained, the same proportional relationship. All I'm really considering is what the effect of on the orbital relationship would be. Now, let's stop there for a break.